All right, hello. So now we're going to go into the world of probability. What are the odds of that? So, probability, you can read all this stuff on your own. I'm going to paraphrase it. But basically, we need to understand probability before we go into the idea of relative frequency and we start talking about normal distributions and we start doing our hypothesis testings and our confidence intervals. So, this is the foundation or part of the foundation for where we're going to be headed. All right. However, before we go into what probability really is and how we use it and how it's applied, we first need to talk about how to count. Okay, and some people look at me kind of weird. It's like, well, why do we have to talk about how to count? It's 1, 2, 3, 4, 5. The issue with counting comes into the idea of repetition. We can't count things twice, or we can't leave possibilities out. So we do need to be very careful and very methodical about how we count things. And there's a whole field of mathematics devoted to this called combinatorics. And that's another story for another day. Actually, it's another story for another day in another class. We're not going to talk about that here, but we're just going to do a cursory explanation of what factorials are, or not factorials, combinations. So to begin, we're going to talk about the counting principle. All right, and what the counting principle says is that if you have a series of events, event 1 all the way out to event m, with possible outcomes of event 1 being n1, and the possible outcomes for event 2, n1 is the number of possible outcomes for event 1, and 2 is the number of outcomes for event 2, n sub m, and so on and so forth for event m. Then the product of all the possible outcomes gives the total possible outcomes for the series of events, where you would have E1 followed by E2 followed by E3, so on and so forth. Okay, so some basic examples here could be the contents of your closet, a locker combination, children in a family. I'll do a few of these. So like the locker combination is an example that we're going to do in a little bit anyway. But like the contents of your closet, if you were to think about the number of tops you have, number of bottoms, and shoes. Okay, we could say hypothetically somebody has 50 tops. That can be sweatshirts, t-shirts, hoodies, whatever. I mean, just 50. For bottoms, I'll go a little more conservative. Say we're going to go with 32 bottoms. And shoes, I don't know, I have a fairly modest number of shoes. Not to make fun of my wife, she has a lot more than I do. So for shoes, we'll go with a number like 6. Okay, so if we wanted to find out possible outfits, all right, what we'd need to do is just simply multiply. It'd be 50 times 32 times 6. So there would be a total of 9,600 possible outfits a person could wear simply by multiplying all these numbers out. Which, by the way, if we were to divide this by 365, that's 26 years. If you divide this by 365, you end up with 26 years of distinct outfits without ever repeating the same outfit twice. But that would be, a white dress shirt, a pair of black dress pants, and then brown shoes, white dress shirt, black dress pants, a pair of sneakers. So once you change the shoes, that changes the outfit. So, but you have options. So when you say, "Oh, I've got nothing to wear," I beg to differ. Children in a family. Let's say hypothetically a family is going to have 3 children. Okay. So you have child 1, child 2, child 3. All right, and for argument's sake, just to keep things simple, we're going to say there's only two possible genders. It can be a boy or a girl. It could be a boy or a girl. It could be a boy or a girl. You end up with 8 possible ways that you can have boys and girls, or plan your family accordingly. Not that there is much planning when it comes to this kind of stuff. So another way to look at this is that you can do what's called a tree diagram. All right, tree diagram, which really is just a way to organize a sample space. You can think of child 1 could be a boy or a girl. There's child 1. Then after you have child 1, you could have another boy or another girl, child 2. And here you could have a boy or a girl for child 2. And then from here you can break off with a boy or a girl, boy or a girl, boy or a girl, boy or a girl. This would be the child 3 branch. So if you look at the different ways this can be arranged, it could be boy, boy, boy. We could do boy, boy, girl, boy, girl, boy, boy, girl, girl. So that's just following branch 1, branch 2, branch 3, branch 4. Then you could go girl, boy, boy, girl, boy, girl, 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 boy, or all girls. Okay? So those are all the different ways that you can arrange 3 children within a family. Okay? So this is a tree diagram, and over here is our sample space. Okay, and this is what I'm talking about with the counting, because you want to make sure that you have every single possibility accounted for. Because if you miss something, that can throw all your calculations off later on when you start to do other things. So that's the counting principle, just simple multiplication. Which now brings us to the idea of factorials, combinations, and permutations. So these all kind of fit into the same family. All right, so we're first going to talk about a factorial. All right, so a factorial is denoted by an exclamation point. So for instance, if we wanted to do 4 factorial, that's simply 4 times 3 times 2 times 1, for a number like 24. So whatever your factorial is, you're going to start with that number, and then you're going to count down by 1 until you reach 1, and then you're all done. Okay, so for any whole number n factorial is n times n minus 1 times n minus 2 times 1, and so on. Okay, some things that you should know: 1 factorial is 1. And 0 factorial is also 1. All right, this one sometimes confuses people because if you think about ways to do something, if you only have one thing to do, there's only one way to do it. All right, so if I had 1 flower, there's only one way to put 1 flower in 1 vase. Okay. Whereas if I had no flowers, there's only one way not to put any flowers in a vase, and that's to not do it. So not doing something counts as a way of doing something. You have to account for nothing. Okay? So that's why 0 factorial is 1. So for instance, we could use this factorial for trying to figure out the ways that 6 runners can finish in a race. All right, so if you think about it, we have 6 runners in a race, so we can do 1st, 2nd, 3rd, 4th, 5th, and 6th. How many runners do we have for 1st place? Well, 6 runners can come in 1st place. Then how many runners can come in 2nd place? Well, one of the runners already finished, so that would mean that there's 5 remaining. Now that 2 have come in, for 3rd place, there's only a choice for 4. For fourth place, there's only 3 because the other 3 have already finished. Now it's a race for last. Only 2 people can come in second to last, and only 1 person can come in last. So this is the same thing as 6 factorial, which equals 720. All right. There are ways to do this in the calculator. If you're going to do this in your calculator, it's math, the math button, and then you're going to go over to PROB, prob, or PRB, depending upon, and the factorial is option 4. Okay, so math, PRB, and factorial is option 4. So now we'll take a moment to go into permutations. So factorials and permutations are, in my opinion, very, very closely related because it's only part of a factorial. And I'll show you how that works through an example. So basically the thing is that when you're dealing with a permutation, order matters, all right? We're putting only a select subset and putting them in order. So there's a ranking, okay? It's a specific arrangement, all right? So here's the definition and here's your formula, okay? In your calculator, you're gonna push the math button, then you're gonna go over to PRB, and it's option 2, NPR. So you're going to type your N in first, then you're going to do the math stuff, and then you're going to type your PRB in. Okay? And your trials has to be larger than the number that you're going to select. So, if we were to go back to our 6 runners in a race, now we're only concerned with how they can finish first, second, and third. Okay, so if we think about this using if we do this using NPR, it would be P6, 3. When you type this into your calculator, you get a number of 120. Okay, an alternative way to do this, I'll do it in a different color, all right? An alternative way to do this, all right, we have 6 runners, but we want to know first, second, and third. Well, we have 6 people coming in first. We have 5 people coming in second. We have 4 people coming in third. If you multiply 6 times 5 times 4, you end up with 120. Okay? So, I mean, when I was a student, the way I used to do these was that when it would be 6, choose 3, I would just start with 6 and only go out 3, and it always worked for me. It turns out there was a formula for it, and I never knew that. But then again, we're going back to when I was in high school. Always looking for a shortcut, another way to do it. This can also be used if you go to Saratoga, or if you're going to go to, well, nobody goes to Saratoga now. If you're going to go to the OTB, this would be a exacta bet, I think. Exact is when you pick them coming in a specific order. So permutations would be exactas, combinations would be, no, I take that back. This would be a trifecta. This would be a trifecta because that's when you're picking 3 coming in first, second, third. The exacta box is a combination. Sorry about that. Hope I didn't confuse anybody. So now that I've gone into the segue of a combination is when order isn't really that important. We just want to know the number of different ways that we can group things together. So if you were to compare the combination to the permutation, the combination eliminates all the repetitions. So if we were looking at just the letters A, B, C, ABC is the same as BAC, which is the same thing as CAB, which would be the same thing as CBA. All four of these would be logically equivalent in a combination. So these guys would count once. Whereas if you go up back to where we were with the permutations, these would be four different things. So as a result, combinations typically have a fewer number of arrangements or outcomes. So, and here's the formula for it. Okay, I'm not going to make you use the formula. In your calculator, it's math PROB option 3. Option 3 NCR. Yeah. So you're packing books for a flight and you can only fit 3 books in your carry-on bag. You have 6 books to choose you have 6 books to choose and you can only bring 3 books on the flight. How many different ways can you choose 3 books from the 6? So that would be 6 choose 3, which ends up giving us an answer of 20. Okay. Here, you know what? I'll show you quick in the calculator how to do this. So for all of these, you would type in the number 6, math, go over to probability, go down to option 3, and it's 6 choose 3. And there's your answer of 20 that you get. Ignore all that other stuff up there. Okay. So I have a little closing thought here. How can we determine the number of outcomes of an experiment? So if the experiment consists of a series of stages with various outcomes, use the fundamental counting principle or a tree diagram. If the outcome consists of ordered subgroups of R items taken from a group of N, the idea is ordered subgroups. If they're ordered subgroups, then you're going to use your permutation rule. If it's non-ordered subgroups, there's your combination rule. Okay. I'm going to pause this here because it's been 17 minutes. Our next video will go over these examples for us to work on together. So if you want and you think you understand what's going on, try these before moving on to the next video.